This is our second lecture in topology. The second lecture is going to be on something called metric spaces. I'm going to remind the listeners again, the audience, that if you are a student in my class, then the assignments that accompany every single lecture, they can be found on the course pages. But if you're watching this off of a streaming platform, then those assignments will be located in the video description, so you can find them there. I'm not going to make a comment about that in any of the other lectures, but it's important, so figured I should say it at the beginning of this lecture. So this lecture is going to be on metric spaces. The word metric over here is going to refer to distance, some way of measuring distance. This is not yet topology. The good news is that already by the third lecture, we're going to be doing topology. So this lecture is actually not a requirement. This and the previous lecture are not a requirement to do topology. We could do topology right away. The problem would be is the lack of motivation. It would be far more motivating if you get to see some of the stuff with Euclidean and metric spaces get developed first, so that you have a little bit more of an appreciation for where the definitions are coming from when we start talking about topology. So this is a metric and a space. So the word space generally means, so anytime you see the word space, so space generally means set plus something extra. A set is just a set. A set is just a collection of elements. It could be finite, infinite, uncountable. So that's what a set is. Usually in mathematics, we almost never exclusively just deal with sets by themselves. The reason why we talk about sets a lot is because sets are often the unifying language to what we do in many different math subjects. We kind of bring it back down to sets, and we often use set operations. But if you've noticed, in many math subjects, it's not just a set, there's something extra going on. So it's the something extra that we write. So we would write a space. So we write a space. So we would write, let's say, space, right? So something extra. So we have a space, and then we can have a vector space. So it's a set. It's a set of elements that form a vector space. So it's sort of the abstraction of vectors. Then today we talk about this thing called a metric space. Then there's something called, in real analysis, there's something called a measure space, if you've seen that, and many, many other things. In fact, today we'll mention something called a Banach space and so on. So anytime you see the word space, all it means, it's a set. It's a collection of things, elements. Sometimes you call them points. You can call them elements, you can call them points. And then the quantifier that you put in front of space indicates what kind of additional structure comes along with your set. So that's, here we're going to be talking about the structure of a metric. So let's begin with this. So let's make our definition. We have a definition here. So we would have this. So let X be any set, presumably non-empty, though it could be empty, but then it's really silly. And a metric on X. Maybe I should write it like this, a metric on X. We're defining what a metric is. A metric on X is a mapping. So if you go back to the first lecture, we talked about norms. A norm is a type of mapping on Euclidean space. But now we're no longer talking about Euclidean space. You want to think of today's lecture as this is sort of like a generalization of Euclidean space. So with Euclidean space, we talk about norms and things like that. But when you have an arbitrary set of objects, the concept of a norm is not going to really make a lot of sense. So like, for instance, if you recall, one of the properties of a norm is if you multiply a scalar by x, then you can pull out the scalar and just retain x. But the problem would be is, like this operation over here, the operation of multiplying a scalar by a vector, the reason why this makes sense is because x is a tuple consisting of real numbers, and real numbers can be multiplied by a real number. In general, if this is like a set of anything, of any type of objects, like let's say this is, like we're going to see, for example, you talk about graphs or something. If this is like a graph, it would make absolutely no sense. Like, what does it mean to multiply a graph by a number? So it's like norms do not make sense on an arbitrary set. So that's why we say this is a generalization of Euclidean space. We're not going to use a norm. Instead, we're going to use something else called a metric. So a metric on X is a mapping. So it's a mapping. Now, a norm, if you recall, I just want to show this kind of relationship. So a norm, if you recall, it was a mapping that had a single input, and it took a vector in Rn, and it assigned for you a real number. That's what a norm function was doing. A metric, it's a function that has two inputs. There's two inputs that go into it, as opposed to one, and it's a mapping from X cross itself, so the Cartesian product. So as you all know, this notation means this is the set of pairs where the first coordinate is coming from X and where the second coordinate is coming from X. So both of these, so all this means is that whatever you put in here and whatever you put in here, they're both coming from the set X. So you take a pair of elements in X. You can also call them points. You take a pair of points in X, and then you assign a real number. So that's where the difference lies. Here, you assign a measurement for every vector, but here you need 2 points in order to compute their distance. So it's done a little bit differently. And the following properties are satisfied. So the first property is so we say distance. So you read this, so it's called D for distance. So we're going to keep on saying distance. The distance between 2 points. So we would write that the distance between X and Y, so here a lowercase x and lowercase y, they're elements in X, is bigger than or equal to 0. And okay, so it's bigger than or equal to 0. That's like property number 1. It's very similar to what we have with a norm. And property 2 would say that the distance between X and Y is equal to 0 if and only if X and Y is the same point. So the distance from a point to itself should be 0, and that's the only way this happens. So this first property, this is called positivity. If you recall, we said on our first lecture in mathematics, when we say positive, we often mean non-negative because we get sloppy. This second property, you can call this definiteness. Not sure if that's the best way to call it. And the third property, we have the distance between X and Y should be the same thing as the distance between Y and X. This one is called symmetry. And we have another property. This is the last one. The distance between X and Y is less than or equal to the distance between X and Z plus the distance between Z and Y. And this one is called the triangle inequality. So these are the properties that we want to satisfy when we have a metric. You will notice the homogeneity property, where you factor out a constant, is not present, because, to repeat this again, a metric is not a norm. They're similar, but a metric is something that's a little bit more general than just what a norm is. So this is the definition of a metric. So here it is. And so let me think. I think I have an exercise that I want to write down over here. So yeah, so let me write down this exercise. I want to put this on the homework. So to repeat this again, I'm not going to repeat this in the subsequent lectures. It's going to be the same idea. In the middle of the lecture, I will write down some exercises, and then those exercises will reappear on the problem sets for you to do. The problem sets may also include some new exercises, but the reason why I want to include this exercise in the middle of the lecture is because it nicely fits with the flow of what we're talking about. So here is the exercise. So the exercise here is this. So let norm be any norm on Rn. So pick whatever norm you want. We did remark it in some sense it does not really matter, because open sets, the notion of an open set is invariant regardless of what norm you decide to use. But you pick any norm on Rn, and then you would define the mapping. So we're going to define the following mapping. We're going to call it D, and this is going to be a mapping. Maybe it's a good idea. I always like to write it like this to just reinforce the fact that it takes 2 inputs. So this is a mapping from X cross X into R. And what does this mapping do? So here's how it's going to be defined. So for x and y in Rn. So I realized I'm calling it x. It's better to just call it Rn to avoid confusion. So in this case, our set x is Euclidean space. So you take 2 points in Euclidean space, and then you're going to define their distance. We're going to define the distance between x and y. So this is by definition. This is equal to by definition. So we define how the distance is being calculated. We subtract the two vectors. So the Euclidean space is very special because it consists of real numbers. So this operation makes sense. We can subtract vectors. In general, if you have just a set in general, and you pick something in here x, and you pick something in here y, x minus y will make absolutely no sense. They're not vectors. Like, what does that even mean? But because you're dealing in Euclidean space, this actually has meaning to it. So you can subtract them, and then after you subtract them, you then apply the norm function. And then the exercises show that D is a metric on Rn. So that's the exercise. So we can say this is, you can call this the induced metric from a norm. So you're using a norm to create a metric. So conversely, it is not true. Conversely, it is possible to create metrics on Rn which do not come from a norm. This is not hard at all. I'll show you an example very soon. So the word induced in mathematics, if you've never seen this phrase before, it means coming from something else. You're using a different structure. So you can say this. Induced means using a different type of structure to create a new type of structure. So we've remarked that we have a norm. It's a type of structure on Rn, and then you're using it to create a metric. So a norm is better than a metric, because what this exercise shows is that you can use norms to create metrics, but it's not true the other way around. You can have metrics that do not come from norms, and we'll see an example of that very soon. It's not hard whatsoever. Norms have additional properties which are nicer. Okay, so this is a comment that we wanted to say. I want to give you some examples here. Let me take this down. So here's a very silly example. A very simple, very silly example. But interestingly enough, it comes up a lot. Often as a counter example. So if you ever find yourself in a situation and you're asking the question, is it true that every metric space has this and this property? Often use this example. This is often the counter example to many questions. Not always, but to many questions. So this has a name to it. This is called the discrete metric on any set. This can be done on any set. It does not have to be Euclidean space. It could be any set whatsoever. Just take a random set of objects, no matter what they are, and you can do this. So here's the way this is done. So for x and y in your set x, we define the following distance function. We define the distance between x and y to be equal to 1 if x and y are not the same, and it's equal to 0 if x and y are the same. So yeah, this is called the discrete metric. It only has two values, 1 or 0. So the picture is basically this. You take 2 points anywhere in your set, and if the 2 points are different, the distance is always 1. Otherwise, the 2 points are exactly the same. And if they're exactly the same, you set it equal to 0. So now we can verify the properties. So what kind of properties? So is this a metric? Is this really a metric? It seems a little bit too silly to be a metric. So let's mention the following properties. Positivity. Is it positive? Again, positive, not negative. It always returns 1 or 0. So this is true. Symmetry. Do we have symmetry? If we interchange x and y, yes, it's the same thing, symmetry. We talk about definiteness. Is the distance equal to 0 only when the 2 points are the same, x and y are the same? Well, you can see by the way this is defined, the only way it's equal to 0 if the x and y are the same. So by construction, this is true. So the triangle inequality is the last remaining one. And this one requires a little bit of casework, but otherwise it's very easy. So what you have to do is you're going to pick any x, y, z, and then you're going to check. So these are x, y, z in x, and you have to check whether the distance between x and y is less than or equal to the distance between x and z plus the distance between z and y. That's what you have to check. And in order to accomplish this, you have to do this by cases. So let's say that x and y are equal to each other. Well, if x and y are equal to each other, then this is 0. And then it does not matter what this is. This is either 0 and 1 or 0 and 1, and then you win. 0 is less than whatever that is. Right? So if x and y are equal to each other, then that's 0. Okay. So then the other possibility is x and y are not equal to each other. Then that would be 1. So that's the second case. So if x and y are not equal to each other, then this is 1. So now if z is equal to x, this would be 0. And if z is equal to y, that would be, so the only way, so basically the possibilities are this. If x and y are equal, then there's nothing to prove. This is 0, it does not matter what this is. The other possibility is x and y are different. And if they're different, this is 1. The discrete metric is equal to 1. But then the possibilities that we need to check are 0, 0, 1, 0, 0, 1, and then 1, 1. Now you can see in these three cases, 1 plus 1, 0 plus 1, and 1 plus 1, they're both greater than or equal to 1. So then we win. So the only way we can potentially have a problem is if we have something like this. When this is equal to 1, but this is 0 and this is 0. But if this is 0, then this is another way of saying x is equal to y. I'm sorry, x is equal to z. And this is another way of saying y is equal to z is equal to y. But if x is equal to z and z is equal to y, then it means x and y are the same. But then this would not be 1, that would be 0. So that never happened. So that's basically what that comes down to. It's not a very exciting proof. In fact, we'd not even write it out in sentences because it's just so straightforward. It's basically just verifying the different kinds of cases and seeing that in every possibility, the metric space properties are being satisfied. So now, so that's called the discrete metric. So as a result, well, actually, let me say what a metric space is. That's the next thing that I want to move to. So the next thing is, let's talk about a metric space. So we just gave an example of a metric. Now I want to give an example of a metric space. It's actually very simple. So a metric space, and we write it as a pair, x comma d, consists of a set x. So you need to have a set and a metric and a metric d on this set. Okay, so we have a metric and we have a space. So we have a set with this additional property, and the additional property is we have a distance function. So that's what we call a metric space. So this is a metric space. So let me give you some examples of metric spaces. So here's some examples. So some examples. Now you can come up with infinitely many examples. So some examples of metric spaces. So let x be the set of continuous functions, so continuous in a calculus sense, that map the closed unit interval into the, so it's just, all it means, in other words, you're considering functions that go from 0, 1 into R. So there's no bound, to how big these functions get. But they're all defined on this closed unit interval. And these are continuous functions. So we can visualize. So let's try to visualize how the set looks like. So we can visualize x. I think this will make it easier to understand what's going on. We can visualize x as curves defined over that interval. So we're going to draw this picture. We're going to draw our interval from 0 to 1. Okay, that's our interval from 0 to 1. So this is our horizontal axis. And then we have r, that's our vertical axis, like this. And then an element, so an element of x is a function. So x consists of functions. So for example, this over here, this function would be one such element. This entire function is an element of x. Right? We're not saying that the function evaluated at some number. We're looking at this entire thing as an element of x. So you can visualize, so this is like a curve, right? Continuous curve. And this entire thing is part of x. Another example of a function would be, let's say, something that just goes like a straight line. It could be a straight line, right? This can be g. So g is also in x. You can also, now you cannot have anything that escapes out to infinity, because as you know from calculus, if you're defined on a closed interval like this, it has to be bounded. It has to reach a maximum and a minimum. So maybe that's the maximum, maybe this is the minimum, and then it could do very strange behaviors or whatever. It can even have sharp corners, it does not matter. It just has to be continuous. This is h is also in x, and so on. So this is a fairly complicated set. I mean, like, try to imagine all possible curves you could potentially have. There's an infinite number of them. You can twist them in any way you want, and that's what x is. And now what we do next is, this is a set, and we want to give it a metric. So here is, so let f and g be elements of x. So again, if you want to visualize it, you think of f and g as two of these curves. There's an infinite number of curves you can pick. You just take two of these, and we're going to define a metric, and I'm going to call this metric d subscript s. S will stand for supremum. And this is the way we're going to define it. So we're going to say the distance, the supremum distance between f and g is going to be defined as follows. So this is going to be equal to, by definition, it's going to be equal to this. It's going to be equal to, we're going to do f of x minus g of x in absolute value. And then we're going to consider the supremum as x ranges over the entire domain. So to draw a picture, I think this will clarify what's going on. We have one type of curve, this is f. We have another type of curve, this is g. And the way we calculate the distance between them is, basically what we do is we calculate these vertical distances, these vertical displacements. So this is being done in absolute value. It's like we're subtracting, we're just looking at the positive distance between them, right? These vertical displacements, f of x minus g of x. So we're letting x range over this interval, so these are the vertical displacements, and we're finding which one is the largest it ever gets. Now, just some comment here. I'll add this comment from calculus. Know that the supremum exists and is a finite number because you have continuous functions. This is, I guess you call this the extreme value theorem from calculus, that if you have a continuous function, it reaches a maximum and a minimum, so things do not escape out to infinity. And in fact, if you want to, you do not have to, but if you want to, you can even replace the word sup by max, because that's part of the extreme value theorem. The extreme value theorem would say that if you're defined on this closed interval, then the function achieves its supremum. So there's a difference between a supremum and a maximum. The maximum may not exist, but the supremum exists. But like in general, when you're doing like general stuff in advanced calculus, but here, because of the extreme value theorem, you can even talk about the maximum displacement. The maximum exists, but it does not really matter. So I'm going to call it ds, where this is the supremum distance. The supremum distance. So that is one way of doing it. And then we can have di f, and g. This is going to be an integration distance. So this is going to be equal to, by definition, we're going to do something very similar. We're going to do f of x minus g of x, and then we're going to integrate this from 0 to 1. And because the functions are continuous, so I want to remind you this set x, it would probably be helpful if I written it right over here. So this set x, this is the set of continuous functions from 0, 1 into R. So all of these functions are assumed to be continuous. This is the reason why it's important to confine ourselves to continuous functions. If these were functions in general, then these kinds of metrics would not even be defined, because then it would be conceivable that maybe soup is like infinite or something like that. We want to have real numbers. So these would be our metrics. So we have this as well. This is the integration distance. So the way you visualize the integration metric is you do the same thing. So x ranges from 0 to 1. So you have these vertical displacements, but instead of finding the maximum vertical displacement that you see, you find the area between the two curves. That's what this is. So this is the way you can interpret this is this is the absolute, so in absolute value, the absolute area between the two curves. So it's not like it's positive here and negative there. It's just only positive area that exists between the two curves. And as an exercise, so here's an exercise. You want to show that ds and di are metrics, right? They're different metrics. They're metrics defined on this set x. And so x comma ds and x comma di are metric spaces. So you have two different metric spaces. It's the same set, but here you have one metric and here you have a different metric. So you have two different metric spaces. For the next example, let's do an example that involves graphs. Let G be a finite connected graph. So I do not want to define what is a graph because that's going to take us off topic. If later in the semester we have to give a more rigorous definition of a graph, we will do it. And I do not want to say what it means to be connected. Later on in the class, we'll define what it means to be connected, but you can talk about a connected graph. So basically, something that looks like this. You have a bunch of vertices. Basically, this is what we're saying. You have a bunch of vertices, and then these vertices are connected by some kind of edges. They do not have to be lines. They can be curved or whatever they are. This one, maybe this one goes underneath that one. This one goes like this, and this one goes like that. And maybe this one goes underneath those two. So this is what we call a graph. It is a collection of vertices, and then you have edges, not necessarily straight lines, though we usually draw them as straight lines, that connect them. This is just to indicate that they're not intersecting, that this sort of goes underneath that one. That's all what that means. You can be more sloppy, and you can just draw that, and then you emphasize the vertices by making them solid color. But I'll keep it like this. And we're going to let x be the vertex set of G. So you give these names like 1, 2, 3, 4, 5, 6, 7, 8, 9. So you give these names. And when we say we have a finite graph, what we mean to say is the vertex set is a finite set. And what we'll do next is we're going to define the following distance. This is another example of a metric. You would say that the distance between x and y is the minimal number of edges required to get from x to y. So like, what would be the distance between 4 and 7? So you cannot, well, the distance between 4 and 7, you can use a single edge. So that would just be 1. It's the minimum way to do it. You can also get from 4 to 7 in the more complicated way. You can travel from 4 to 3, from 3 to 5, from 5 back to 4, and then 4 back to 7. So, but you want the minimal number of edges required. if it's the same vertex, let's say 8 and 8, the distance between 8 and 8 would be 0 because there's no, you're already located at 8. You do not need any edges. So yeah, this is the distance function that you have, and one can show, so it's clear, so clearly all metric properties are satisfied, and maybe the one that takes some work, and then the one which takes some work to justify is the triangle inequality. I mean, it's clear that it's symmetric. If you can get from x to y, you can just reverse your path backwards. So that's rather straightforward to see. So the triangle inequality is the one that takes some work. Now, I do want to make a comment here that I should have said earlier. We're talking about a connected graph. So connected graph basically means that there's a way to get from one vertex to the other vertex. An example of a graph that would not be connected is if we were to remove this edge, let's say remove this edge, let's remove this edge, let's also remove this one. So this right here would be a graph. Let's do it like this, let's say. So this would be a graph that is disconnected because there's no way to get from this vertex to any other vertex. And then the distance function would be undefined. Also, another interesting observation about this distance function is that it always returns an integer. It's very similar to the discrete metric that always returns 0 or 1, but this one is not the discrete metric. It could return back other types of integers. So it's the triangle inequality that takes some work to justify. So what we need to show is let x, y, and z be elements of x. This is the vertex set. And we want to show that if the distance from x to, let's say, y is always less than or equal to the distance between x to z plus the distance between y to z. So how do you prove this? Here's how you prove this. So say that the distance between x and z is equal to some number n, some integer n, and the distance between y and z is equal to some integer, let's call it m. So there is a path of edges from x to z. There is a path of n edges from x to z. So if the distance between x and z is n, you can find some path that will take you from x to z, and you're using n edges in that path. And then there is a path from there is a path with m edges from z to y. So now you put the two paths together. So now by continuing paths, so the picture here is very simple. Here you have x, here you have z, and you have some kind of path of n edges, and then you have z and you have y, and then you have another path consisting of m edges. So if you travel along this path and then you travel along that path, then you just found a path from x to y that consists of m edges and m more edges. So by continuing paths, we can find a path from x to y consisting of n plus m edges. Therefore, the distance between x and y, which is by definition the minimum, this is the minimum number, this is the minimal number of edges from x to y, is less than or equal to n plus m. Because the distance function on a graph, on the vertices of the graph, is defined to be the shortest possible path. So if it's the shortest possible path, this path that we just drew is not necessarily the shortest possible path. There might be a shorter path. It is some path, but it's not necessarily the most optimal one. So therefore, the distance between x and y, which is defined to be the minimal number of edges, is certainly going to be smaller than or equal to whatever number that is. And so now what is n plus m? N plus m. N is the distance between x and z, and m is the distance between y and z. And then look at that. The distance between x and y is less than or equal to this, and that's the triangle inequality. So that's how you would prove the triangle inequality for this distance function on the vertices of some kind of graph, on a connected graph, I should say. So now let's talk about open disks. That's the next thing. Here's our next definition. So in this definition, so let X, comma D be any metric space. So you can go back to any of the previous examples we've looked at. So take any metric space, and then for a point in X, and by the way, when I say a point, I mean an abstract point. If X is a set consisting of functions, then a point is probably more appropriately denoted like this, a point. It's just an abstract point, it's just an element of a set. The way that point looks like can be quite complicated, but a point, for a point in X and epsilon bigger than 0, we define the disk B epsilon. This is the open disk of radius epsilon. Some people write B, P epsilon for the open ball, I guess. I think maybe, I'm not sure what Moncrief does. I've seen some people denote this as delta P epsilon, delta for disk. I've seen some people do it like this. And then some people write it, they write like a ball, then they write subscript P epsilon, and then I've seen some people write it like this. So there's like an infinite number of different permutations of these you can do. It's just like no matter who you ask, everyone has a slightly different notation. So if you want to use your own notation, you can do it as long as it's clear what you're doing. Usually what people do in topology and in metric spaces and all that stuff, whenever you write something, if you're writing a paper or whatever it is, when you write something, you usually indicate your notation at the very beginning so people know what you're saying. So this is what we're going to say. This is called the open disk. This is the open disk that's centered at P of radius epsilon. It's very similar to how we did it with Euclidean spaces. In Euclidean spaces, you probably recall, we said X in Rn. Well, now the difference is this is X in R set X with the property that sometimes people indicate that and sometimes people write that. The only reason why I wrote that last time is because when you use norm symbol and then you have another bar, that looks pretty bad. But I generally write it like this. So X in X with the property that's what this bar means, that the distance between X and P, previously we kind of written it like this, X minus P. But more generally, when you have a metric space, you're saying the distance between X and P, you want that to be less than epsilon. So you call that the open disk. You can also call this the open ball. If you want to be very confusing, you can call that maybe the open interval or whatever you want to call that. So, okay, so we have this, the open disk. Now, okay, so this is our metric space. This is our open disk. And maybe we can just illustrate some examples of an open disk. So let's just indicate some examples. I'm going to take this definition down, and we'll look at some examples. Examples of open disks. So in the first example that we're going to look at, X is any set. And D over here, this is the discrete metric. So to remind you, the discrete metric, the way it works is if you take two different points in X, their distance is automatically 1, no matter what they are. If the 2 points are the same, then their distance is 0. That's what we call the discrete metric. So how does an open disk look like? Well, the open disk centered at some point P of radius epsilon would be equal to its X in X with the property that the distance between X and P is less than epsilon. So let's say that epsilon is equal to 1. So let's say we make this epsilon equal to 1. Then the open disk of radius 1 would consist of all points whose distance is less than 1. Well, just think of it like this. The discrete metric only gives you two possible values, 0 or 1. It cannot be equal to 1 because 1 is not smaller than 1. So the only point whose distance will be smaller than 1 is when the distance is 0. And the only time that happens is when X is equal to P itself. And so this would just consist of a single point. It's just a single point consisting of just P and only P and nothing else. However, and by the way, this will also be true if you pick epsilon to be 1/2. That would also be just P itself. However, if you pick epsilon to be something bigger than 1, let's say 2, then now you're saying it's all points whose distance is less than 2. Well, the discrete metric returns 0 or 1. No matter what it is, it will always be less than 2. And so, in this case, this is the set of everything. This is X. So this is an extreme example. You have like the smallest possible disk, right? Disk will always contain its center, but in this case, it's just its center and nothing else. And then this is like the biggest possible disk where it contains everything. So it's a fairly silly example. It's a very strange behavior of an open disk, but it nicely illustrates the definitions and how they're being used. We have to show how the definitions are being used. So this is our first example of an open disk. Let's look at another example. So in this example, this is example 2, X is going to be the set of continuous functions that map this closed interval into the real line. And D over here is going to be the supremum distance. So the way the supremum distance is defined is that if you pick two functions, so f and g are two functions in this set, so these are two continuous functions defined from 0, 1. What you do is you do f of x minus g of x, so you calculate the vertical displacement and absolute value, and then you calculate the supremum that you get as you range over this closed interval. And that would be your vertical displacement. So let's draw a picture. Let's draw a picture for the disk that is centered at some point. Okay, so again, point in quotation marks. This is an abstract point, a point in the set. A point in the set is a function. So let's pick a function in this set, and let's pick the easiest function that there is, the 0 function. So I'll just write, I want to make like a really, really bold 0 or something. This is the 0 function. Not the number 0, but the 0 function. This is the function that maps everything to 0. And let's say we make epsilon be equal to 1. So let's draw a picture for how this open disk looks like. So we're going to draw the interval from 0 to 1, and we're going to draw the 0 function. So this is the 0 function. It's here. This is the 0 function. So it's just completely flat. And this, by definition, this is the set of all points. Let's call them f in x. So it's all functions with the property that the supremum distance between f and the 0 function is less than 1. So the vertical displacement has to be less than 1. So let's draw the vertical displacement. Now, because we have the 0 function here, it's very easy to draw the vertical displacement. The vertical displacement only goes up to 1. So we're going to draw this. So this is exactly 1 unit. And then we're going to draw this in the other direction, because we are using absolute value, of course. This is one unit in the other direction. And then we're going to fill in, and then the way this looks like, so it's hard to, I do not want to fill in the square. That would be that would not be correct. So I'm going to draw this, and then the way this looks like, it's not really possible to visualize this because this is such a large set, but basically every single function in that open disk, it has to fit somewhere inside this window. So every function, its vertical displacement from the 0 function has to be less than 1. So all functions that fit in that window. So for example, this would be one such function. That would be another function. All continuous functions that fit in that window. Okay, so as long as they're fitting in that window, that's how it looks like. Okay, you do not want to just draw the square and say that's the picture of that set, because I mean you're drawing individual functions. So together, these are just some of them. Okay, that's just how some of them look like. Now we also have another metric. It's the integration metric. So the integration metric between two functions, you calculate the integral from 0 to 1 of f of x minus g of x, and you calculate that. Well, you can find functions in the integration metric. So I'll write it over here. So you can find examples of functions f such that the distance between the integration distance between f and the 0 function is less than 1, but actually, yeah, it's less than 1, but the supremum metric between f and the 0 function is bigger than 1. So in other words, it kind of illustrates how different these two metrics are, that here the function, the vertical displacement goes above 1, whereas the integration metric, the area between the curve, is less than 1. So for example, so I'll just draw an example just to show what I mean. So here's 1. So what you can do is you draw it really, really high up, and then you make it super, super thin. Make it super thin, like this. So that's going to be your function. And then the integral from 0 to 1 of f of x minus the 0 function, that would just be the area underneath the curve. So you can make the area underneath the curve be equal to like a half or something, right? You can imagine of making these two lines so close together that the area that's contained in this triangle is so small that it's less than 1/2. But it can go up to like 100 or something. It can go up to a big number. But the supremum metric between f and the 0 function can be bigger than 1. So it's because we have two different metrics. So the open disk of radius 1, when you're using the supremum metric, you will draw this box, and then every function that belongs to this open disk will be contained within this box. But then you have functions like these that are not contained within this box. So the supremum metric here is greater than 1. So they're not in this open disk. But when you're using the other metric, when you're using the integration metric, they are still small. So that's just another illustration of an open disk. Let's also go back to our graph example. So let's just draw any graph you want. So we have a graph like this, maybe. Let's go ahead and draw this graph. I'm going to make them cross over each other. I'm not going to make a big deal out of it. We understand that if they're crossing over, technically they're going underneath each other. We're just being too lazy to draw that. So we'll draw this graph where we fill in every single edge. And then you have 5 vertices. So let's talk about the open disk that is centered at 1 of, let's say, so this over here, so that's the vertex, and the 2 represents the radius. So you write the point first, and then you write the radius. So this will be x in the vertex set, so that the distance between x and 1 is less than 2. So everything that is less than 2. So that will include 1 itself. It will include 2, because the distance between 1 and 2 is 1. It would include 5. It would also include, so actually I see what the issue is. Yeah, it will include everything, in fact, because there is an edge going directly from 1 to 5. So maybe, to make it more interesting, I should have drawn this, and then get rid of this, and get rid of that one. So maybe that would be a more interesting kind of a picture, because in this picture, then you can see that the distance between 1 and 2 is 1, the distance between 1 and 5 is 1, whereas the distance between 1 and 4 is 2, and the distance between 1 and 3 would be 2. So your open disk here would consist of these 3 points. However, also, the open disk from 1 to 2.5 would be the same thing, because when you're working on the graph distance is always an integer. So you just round it down to the nearest integer. That would be the same thing. But if this number was 3, then that would include all of them. So that's how the open disk looks like. Not the most exciting example. Maybe if you had perhaps, yeah, like maybe if we started adding more vertices and edges, you could make it be slightly more interesting. But we'll just leave it like that. I think that's enough to just illustrate the idea of an open disk. So that's what we call that's what we refer to as an open disk. So now that we have this notion of an open disk, the next thing that we're going to talk about is what is known as an open set. So fortunately, this is very similar to what happens with Euclidean spaces. So let x comma d be a metric space, and let U be a subset of X. We say U is an open set, if and only if for any p in U, there is an epsilon bigger than 0, that the disk, which is centered at p of radius epsilon, is sitting inside this set U. So it's almost the exact same definition as in Euclidean spaces. So from this point on, many of the results are going to be very similar that we saw before. And in fact, many of the proofs are almost the same. Let's start with this. So here's a proposition, which is going to be an exercise to prove that the open disk is open. It's actually almost the very same proof, except there's some changes in the notation because you're no longer using a norm, but you're using a metric, but the idea will remain the same. So open disks satisfy the open property. So this is the open property that for any point, you can find an epsilon so that the disk sits inside U. So that's the definition of an open set. And now that we have defined an open set, we can also define what it means to be a closed set. So you can probably guess what that means. And you would say C is closed if and only if the complement, so this is the complement in X. So instead of Rn, you take the complement in X, is open. And I just have to give the warning that we gave last time, that being closed is not the opposite of being open. So if something is not open, does not automatically mean it is closed. The set could be neither, and a set could be both. For example, the empty set, you just have to carefully run through the definitions, but the empty set is both open and closed at the same time. So they can be both. So strange things like that can happen. And also, another proposition that I want to mention, this is also very similar to before. Also treat this as an exercise, that there's like 4 parts. A finite intersection of open sets is open. A finite union of closed sets is closed. Arbitrary unions of open sets is open. And then you would say arbitrary intersections. So in practice, it's an infinite sequence, but it could be an uncountable collection. So arbitrary intersections of closed sets is closed. So very easy to prove. It's almost the same proof. There's just some changes in notation, but other than that, it's the same thing. So now I want to get to a very important point here, and it's this. Let me take this away. So previously, this is lecture 1, we remarked that all norms on Rn lead to the same topology. In other words, that means more precisely, it means if a set is open with respect to one norm, then it is open with respect to any other norm. So that's what we said, that all norms on Rn lead to the same topology. So you can ask, so here's a reasonable question, do all metrics on X lead to the same topology? So if something is open with respect to one metric, does it mean it is open with respect to another metric? And the answer to this question is no, it is not true. And I'll give you a very easy example of that. There's something just really nice about norms. Norms have so many nice properties that make this possible, but metrics lack a lot of those properties, because you have to understand that a norm is defined on Euclidean space, and Euclidean space consists of real numbers, and real numbers themselves have a lot of wonderful properties. But if you're just talking about a set in general, there's not much more you can say about it. So in fact, I'll give you an example involving the real numbers. So here is a very easy example. So let D be the usual distance on the real line. So this is R1, but the real line. So in other words, the distance between two numbers on the real line is just their difference in absolute value. In fact, this is a norm, right? This is coming. This is just the absolute value norm. So that all this means is that you have x, you have y. You take out a ruler and you just measure how far apart they are. So this is the usual distance. And then you let d, let's say d prime, be the discrete distance, the discrete metric on R. So this would just mean that if you have x and y, no matter how far apart they are, it's always equal to 1. It's always equal to 1. Unless, of course, unless x and y are the same, in which case the distance is 0. So if U is any subset of R, then it is open with respect to D prime. Why? Well, here's why. You're going to pick any point in U. So then the disk that is centered at P, and you pick epsilon to be equal to 1/2, that would just be, the disk here is just a set containing P itself. This is going back to our discrete, open disk example, that if the epsilon is chosen to be 1 or below, then the open disk just consists of P. So the open disk, which is set of radius 1/2 that is centered at P, which is just the point containing P, is a subset of U, because P is in U already. So it's a subset of U. And so what does that mean? So hence, U is open with respect to D prime. So maybe to use perhaps slightly better notation, I should have called this the open disk with respect to D prime, and this is the open disk with respect to D prime. So this is the crucial point. If you pick any subset, it's automatically, any subset of R is an open, it's open. Any subset of R is automatically open. So the open subsets of R with respect to the discrete metric is everything. Like, they're all open. However, let's say the set containing 0, let's say, is not open with respect to the regular absolute value, right? So like you can see this in the picture. If you draw 0, how do you check if 0 is open? The set containing 0 is open. Well, you have to draw an open disk. But when you draw an open disk, you're drawing this open interval, and you can see that no matter how small you make that epsilon, it has to be a positive number. No matter how small you make that epsilon, you can never make it be small enough so that open interval is sitting inside the singleton set. So the set that contains 0, this is an open set. This is an open subset of R when you use the discrete metric, because everything's an open subset. But it's not an open subset of R when you use the regular absolute value metric. So it shows that whether something is open or not open actually does matter on the kind of metric you use. So here you have many, many different kinds of metrics. So this is just no longer true. So now I want to switch the next topic and discuss these things called continuous maps. So now we're going to define what it means to be a continuous mapping. So let's just review from calculus. Let's say we have a function from the real line to the real line. So we say that f is continuous at a point P. It means that for any epsilon bigger than 0, there is delta bigger than 0, so that if x minus p is less than delta, then f of x minus f of p is less than epsilon. So that is what continuity is. This is the way we learn about it in calculus. That's the definition of a continuous function. And now we're going to extend this definition to metric spaces. So suppose you have a function from one metric space So we have x, and we have y, and here x comma d, and y comma, let's call it d prime, because of course these could be two very different metrics, are metric spaces. So you have two metric spaces. You have one metric on x, you have another metric on y, and then you say a function from this metric space to that metric space is continuous at p, so it's continuous at a certain point. So it's continuous at p at x. It's almost the same thing for any epsilon bigger than 0. There is a delta bigger than 0, so that if, now instead of writing x minus p less than delta, I'm going to write it like that. You're going to say that if the distance between x and p is less than delta, and maybe you can emphasize, it's not really required, but I think it's just helpful. You say and x is an x, it's just to reinforce the fact that this x is coming from that set, but it should be clear because this is the metric that goes along with x. So if x minus p is less than delta, so because p is a point over here, x has to be a point in this set. So if x minus p is less than delta, then f of x, and here you're going to write it like this, you're going to write then the distance, let's call it d prime, between f of x and f of p is less than epsilon. So f of x, this is, let's just indicate this is in y, and this is something that's in y. So now you have, because f is a mapping, it maps points to points in y. So this is something in y, this is something in y, and whatever those 2 points are in y, you can measure their distance using the other metric that you have. And that's what it means to be a continuous function between two metric spaces. As you can see, it's almost the exact same definition that one does in calculus, except you just use a different type of metric. So let's maybe give a little bit of intuition. This is sort of like a picture for what's going on. I'm going to draw this square as representing x. I'm going to draw a triangle as representing y. I have no idea how they look like, but let's just draw that. In general, they're so abstract. They can be so abstract that there's not necessarily a way how you can visualize it. It's just that you can visualize it in simpler cases, and then you push that into intuition to more abstract situations. But anyway, this is what we have. And when we say it's continuous at this point p, we look at where that point is being mapped to. Let's say this is f of p. And the idea is basically that if we draw something really, so this is sort of everything that's with it. You see, this over here is f of p. So what we're basically trying to say is that if we make this radius small enough, no matter how small we make this radius, smaller than epsilon, this one gets mapped to that one. Yeah, I'm not sure if this is perhaps the best way. I think maybe the best way actually is just to, because the real intuition, I'm not sure if this gives you the best intuition, because like there's a lot more intuition for what continuous means in a calculus class. So you get a lot of intuition from a calculus class, and then you're sort of saying the exact same thing all over again, except you're just using metrics as opposed to absolute value. So maybe drawing that picture is not exactly the most helpful thing. So so that's what it means to be continuous. And now I'm going to give you an example. This is going to be a somewhat interesting example, slightly bizarre example, but we like bizarre examples, so we're going to like this one. So here's going to be our example. So we're going to let x, this is going to be the real line, and the distance function that we're going to use here, this is going to be the usual distance. So this is the distance where you take the difference of the 2 points in absolute value. And then y is going to be actually the exact same set, but with a different metric. Here the metric, this is going to be the discrete metric. And we're going to have a function from x to y. So I could write from r to r, but that could be a little bit confusing because even though it's the same set, they do have different metrics. So by writing x to y, when I write x, we're referring to the real line with that metric, and when we write y, we're referring again to the real line, but with a different metric. So we're going to have a function, and this is going to be the identity function. So f of x is equal to x. So this is, of course, the identity function. This is the identity function. And so this function is continuous at any point. So if it's continuous at any point, you just say continuous. So that's what we say. So when you say continuous, it just means it's continuous anywhere you want it to be. So in the definition, we're saying what it means to be continuous at a single point, but usually when we talk about continuous functions, we want our functions to be continuous at any point, no matter which one you pick. That's generally the way it's used. So the definition is done at a single point, but it's in practice, the functions are continuous at any point. So this function is going to be continuous at any point. So now why is this? So let's see why that is. So here's the way we do this. So let P be anything in X. So this is, of course, a real number, because X is the set of real numbers. And let epsilon be bigger than 0. We're going to choose, so it's just like a proof in advanced, it's just like an advanced calculus proof. You choose you pick an epsilon and you argue that you can find the matching delta. So here we're using the, let me actually change this up a little bit. So I written this example backwards. I meant to say that X has the discrete metric. This is the discrete distance, and this is the usual. This is the usual metric. That's the one that we normally use. So that's what I meant to say. So X has this unusual discrete metric, and Y has the usual distance between two numbers that we use. And the claim is this function is continuous. So when we say continuous, it means continuous no matter what point you pick. So you pick any point, we're going to show it's continuous. And just like every proof goes in advanced calculus, you pick an epsilon, and now you need to find the delta. And the delta that we're going to use here is going to be 1/2, because if you recall, strange things happen with the discrete metric when it starts getting less than 1/2. So we choose delta to be equal to 1/2. So we argue that if X is an X, and the distance between X and P is less than 1/2, is less than delta, then the distance, so d prime, that's the other metric, between f of X and f of P is less than epsilon. So let's see what this is. Now, if the distance is less than 1/2, then that's another way of saying X is equal to P. And the function, it's the identity function. So do not forget, this is the identity function. This is the function that's equal to X. So this is the identity function. So that's just X, and that's just P. But we just said that if delta is equal to 1/2, then the distance between X and P, if the distance between X and P is less than 1/2, with the discrete metric, the only point that does this is when X is equal to P itself. But then these are equal. And if these are equal, then the d prime distance between them is equal to 0. And 0 is certainly less than epsilon. So that means it's continuous. So that's what this shows. So the identity function from X to Y is continuous. And now you can ask the question in reverse. So this is what makes this example quite interesting. What if you go in reverse? So now let's go in reverse. So now let's say we have the function going from Y to X. Technically, it's the exact same function because X and Y are equal to each, as a set, they're equal to each other. The only difference is we use different letters to just understand we're using different metrics. So the function from Y to X, defined by the exact same rule. And then it can be shown this function is not continuous at any point. So it's like discontinuous everywhere, no matter what point you pick. So something very strange happens when you interchange the two metrics and you go the other way around. So I think maybe this would be a good homework exercise for you to think about that, to try to see if you can give an explanation to why it is not continuous when you So they're both the real line, but if you map it from the real line when you're using the usual metric to the real line where you use the discrete metric, then what goes wrong? Why is it discontinuous? So that's something for you to think about. It's not very difficult, but it's very good practice in checking this definition of continuity. I want to give you another example. So this is like another interesting example to show you. So here's another example of continuity. Perhaps this one's a little bit more interesting. I'm not sure if you thought the other one is interesting. Maybe the other one was a little bit too silly. But in this example, let x comma d be any metric space. So pick any metric space you want. And let's say this. So fix a point. Let's call it x0 in x. So you fix a point. And now you're going to define the following function. You're going to define a function from x to r. And the function is going to be defined by the rule that f of x, so you take an element over here, x, that f of x is going to be equal to, by definition, this is the way we define it, it's going to be the distance between x and x0. Okay, so the basic idea is if this square represents x and you have some fixed point x0, then what you're saying is for any point you pick in your set, you just calculate the distance using the metric that you have, and that gives you a number. So this defines a mapping from every point in x with its distance in relation to the fixed point that you picked in the beginning, and so you have a mapping from x to r. And then this is a continuous mapping. This is a continuous function or a continuous mapping. It's the same thing. Continuous function, continuous mapping. And of course, it's understood. Here, R has the usual metric. Whenever you see R in topology or with metrics or anywhere else, I would say 100% of the time, it means the usual metric, right? If they do not say anything, it's always the usual absolute value metric. So the distance between two numbers, let's say A and B, is the difference between them in absolute value. The only time it means something else is when you deliberately go out of the way to put some kind of unusual metric on the real line, but then you explicitly make it clear that you're doing it. If you're not saying it, it's always understood to be the usual metric. So this is this example. We want to show this. So let's give a proof. So we're treating this, we're going to write a proof over here, but this is just for practice. You can, of course, pause the video and see if you can prove this yourself. So we're going to let P be any point in X. We will show F is continuous at P. So when we say continuous mapping, it's understood that when we say something is continuous, we mean regardless of what point you pick, continuous everywhere, right? Continuous everywhere, continuous at P. So you pick an arbitrary point, I'm going to show it's continuous at P. So you're going to let epsilon be positive, and you're going to choose a delta. And here, you can choose delta to actually be epsilon itself. Why? So here's the reason why you can do this. So by the triangle inequality, so let me actually take this back. So we argue that if x is something in our metric space X, and the distance between X and this point P is less than delta, then the distance between f of x and f of p, so the distance here is the absolute value distance, then the distance between f of x and f of p is going to be smaller than epsilon. So here we're claiming you can use the exact same choice for delta. As you know, sometimes it's like epsilon over 2 or epsilon squared, but here you can get away by choosing delta to be epsilon itself. So why does this work? So here's why it works. So by the triangle inequality, so I deliberately wanted to do this exercise because it nicely illustrates how the triangle inequality is being used. So by the triangle inequality, the distance between x and p is, between x and x0 is less than or equal to the distance between x and p plus the distance between p and x0. And you can also do this the other way around. You can say that the distance between x0 and x is less than or equal to the distance between x0 and p. No, but then I'm writing the same thing, right? I'm writing the same thing like I've written on the other line. So I should write this a little bit differently. So let me write it like this. So I can say this is less than or equal to the distance. Well, I'm actually not sure what I need. I'm not sure what I need. So I'm going to figure out the proof in the middle of this. So this is what we're claiming. We argue that if you pick something, so this is the definition of continuity. We're trying to check the definition of continuity. So let's open up what this is. So let's open this up. So let's write this out. So I'm going to use this board over here as I'm going to use this for thinking. This is not part of the proof. I just have no idea how to do it. So I'll use it for thinking. So you see we're writing over here f of x minus f of p. Right, we have this quantity over here. So by definition, this is the distance between x and x0, and this is minus the distance between p and x0, like this, right? Because how is the function being defined? This function is being defined as the distance between x and this fixed point x0. So I'm just opening up what this means. So this is the distance between x and x0, and f of p is the distance between p and x0. And I'm kind of trying to get an inequality that looks a little bit like this, as you can see. There's an absolute value over here. So I think, okay, I see what I have to do. So it'll be clear after I write it out. So then the distance between p and x0 is less than or equal to the distance between p and x plus the distance between x and x0. We have both of these, right? So we have both of these. So that means that the distance between x and x0 minus the distance between x and p is less than or equal to the distance between p and x0. We're kind of rewriting the first one. And actually, not quite what I want. I got a little bit. I want to make it look like this. So the distance between x and x0, I'm going to move this one over to the other side, minus the distance between p and x0 is less than or equal to the distance between x and p. And the distance between p and x0 minus the distance between x and x0 is less than or equal to p, the distance between p and x. Now notice what's going on. The distance between p and x is less than delta. And the distance between, so x and p and x, it's symmetry. So this will also be less than delta. Now, on this line, you have the distance between x and x0 minus p and x0. And on the second line, you have the negative. So both the original and its negative is less than delta. So thus, in absolute value, the distance between x and x0 minus the distance between p and x0 in absolute value, because you have both of them, is less than delta. And now you go back to how this function was defined. Remember, f of x by definition is the distance between x and x0. That's how it was defined at the start of the problem. So I mean, this is the part you do not want to forget. That's how the function was defined. So this is just another way of saying, so this is f of x minus f of p is less than delta, and delta was chosen to be equal to epsilon. So look at this. So look at what we've shown. So let's go back. We've picked the point p. It did not matter what point we picked. And we're going to show that f is continuous at p. So you choose an epsilon bigger than 0, and then you choose delta to be epsilon itself. And now you're going to argue that every point that's within p, that's within delta of p, will satisfy this inequality. Does it satisfy this inequality? Yes, it does, because it's less than delta, but delta is epsilon. So f of x minus f of p is less than epsilon. So we have that, and we have shown that, right? Why is this true? So where are we using that? That if x is in if x is in set x and this condition is satisfied, so we're assuming this condition is satisfied, and this is exactly where we're using it. This is less than delta, this is less than delta, which allows us to conclude that this is less than delta, and then that makes the rest of the proof work out. So this is just like a nice example of continuity, that if you have any metric space and you fix a point, then the function distance from any fixed point will define a continuous function. So that's another example of continuity. So now I want to mention this is like the last main idea about continuous functions. And then that would be a good place to stop. So this is an alternative way to characterize continuity using open sets. So the theorem that we'll finish on, this is sort of the key theorem. This is used in topology all the time. So the key theorem is this. So we say let x comma d and y comma d prime be two metric spaces. And then we say that then a function between x and y is continuous. And usually we talk about continuous functions. It's very rare, it almost never happens that we talk about a function being continuous at just a single point p. That's just the way the definition is set up. But usually, almost exclusively, we always talk about functions being continuous. So we say that the function from x to y is continuous if and only if. So it's going to look a little bit confusing at first, but then we'll draw some pictures, hopefully we'll clarify it, and then we'll prove it. And then we'll be done with this long lecture that turned out being longer than we wanted it to be. So if and only if for any open set U in Y, so for any open subset U, so it's an open subset of Y, F inverse of U is an open subset of X. So I assume you know what this means, the inverse image, but if not, let's just draw a picture. So the picture that goes along with this is, here we have X, here we have Y, and we pick an open set that's living inside Y. We're going to call that open set U. And the inverse image of U, this is the inverse image of U. Some people call this the pre-image of U. Some people they'll also call this the pullback of U. So the pullback of U, the way it is defined is it's exactly what the notation suggests. You're going to look at points in the original set that it's being mapped from, and you're going to find all of the points that map to you. So all of the points in X do not necessarily, when you map them, end up back in U. So there's a smaller region that's contained within X that is taking all of those and sending them to U. And whatever that region is, you call that F inverse of U. We call that the pullback of U. So we write it out as follows: X in set X such that F of X gets mapped to U. That's the way we write it. And we call that the inverse image because it ends up on the other side. There's also something called the forward image, but we're not going to write it down because we do not need it at the moment. So for any set U, so if you pick any open set in U, the inverse image is an open set in X. And the way you can say it is that this is the way I like to say that. The pullback of open sets is open. So this is like a nice sentence to summarize what this is saying. The pullback of open sets is open. You can also do this with closed sets, but maybe that's a good exercise problem. So the pullback of open sets is open, or the pullback of closed sets is open. So it's about pullback. It's not about push forwards. It's we'll see instances of that later on. It's specifically about pulling them back. Open sets have to go back. So how do we prove this? So we want to prove that the inverse image of U is an open subset of X. So here's how we would prove this. Proof. So we're going to only prove one direction, and then you prove the other direction. So let's prove it like this. So we're going to assume the function is continuous, and we're going to show, so we're assuming the function is continuous, we're assuming we have an open set, we have an open subset of Y, And we're going to show that the inverse image is an open subset of X. That's what we're going to show here. So here's the way it goes. To show that F inverse of U is open subset of X, we pick a point P in F inverse of U. So we begin by picking a point. And then what does the definition say for open set? We have to show that no matter what point we pick in this set, you can find the disk that will fit inside it. Then F of P is contained in U, because that's the definition of pullback. If something is in the inverse image, then by definition it means that F of P has to land in U. F of P is in U. But U is open subset of Y. Therefore, you use the definition of open subset. Therefore, there is epsilon bigger than 0, so that the disk that is centered at P of radius epsilon is contained in U. And maybe to even indicate this is with respect to the D prime metric, because there's two different metrics that are going on. There's the metric on X and there's a metric on Y. Here, where Y is an open subset of, U is an open subset of Y, therefore we have to use the D prime metric. This decoration is not necessary, but maybe just to be very careful and like overemphasize it. So we have this. Now, we also know that the function from X to Y is continuous at this point P. It's a continuous function, so it's continuous by definition at every point, namely at P. So there is a delta bigger than 0, such that, now we're just using the definition of continuity, that if the distance, if X is in set X, and the distance between X and P is smaller than delta, then the distance between F of X and F of P is smaller than epsilon. That's just the definition of continuity. Now, let's reformulate this. Okay, so here's what we claim. So we claim that the disk with respect to the D metric, that's the metric on X, that's centered at P of radius delta, sits inside U. I'm sorry, that makes no sense. It sits inside F inverse of U. So to repeat, this is what we're trying to show. The whole proof comes down to showing that F inverse of U is an open subset of X. We want to show this is an open subset. How do you show that something is an open subset by definition? You pick a point in that set, right? We want to show this is open. So we pick P if in F inverse of U, and we want to fit a disk. We want to fit a disk centered at P. So we're claiming that this delta will do it for us. So how do we check this? So we pick something on the left, and the question is this X also an element on the right? That's how you check subset. So you say that if X is in this disk, then by definition it means that the distance between X and P is less than delta, right? That's the way the disk is defined. The open disk, if X belongs to the open disk, then it means the distance using this metric between X and the center of the disk is smaller than delta. But if it's smaller than delta, then this is satisfied. So then F of X, I almost went back, you see, I almost by accident wrote down absolute value. So then D F of X, F of P is less than epsilon. So it means that F of X belongs to the disk that is centered at F of P, the disk that is centered at F of P of radius epsilon, and this is with respect to the D prime metric. This should have been the D prime metric. And I forgot to put the D prime metric over here. This is the metric on Y. Okay, because if this is satisfied, then F of X is in here. F of X is in here. But, and then, so what did we say? F of X is in U, but U is an open subset of Y. Therefore, there is an epsilon bigger than 0 by definition, so that, and it's not P, this should be F of P, of course. This should be F of P This should be f of p, comma, epsilon is a subset of u. And this is a subset of u. This is a subset of u. Hence, x is an element of f inverse of u, right? By definition. It's in the pullback because f of x lands in u. So x is an element of f inverse of u. And that's what we've proven. You see, we've shown that if you pick something on the left, right, you pick x on the left, then that very same x is also an element on the right. So we have shown that this is indeed an open set. Now you might find this confusing, right? When you first, if you've never seen this before, this looks very confusing, but it is a lot better than using metrics. This is much more flexible type of property to use, and this is the main property that we're going to be using in topology. In fact, it's a lot of motivation what we're doing here for what we're about to see in topology. So we're going to conclude this lecture. We've said all of the important points about this lecture, and then you can look at the exercise problems that will expand upon this and give you some additional things to work through. And then next lecture, by lecture 3, we'll actually start with topological spaces. So topological spaces, they're the ones that get rid of metrics.